Okay, in this video, we're going to look at stress concentrations, do a few examples, and then get into area shape factor and find a design factor. Okay, so if we look right here, there are certain conditions where you have fillets that are going to create a stress concentration, a point where the stress is going to be higher. Okay. And depending on the situation, we can find those maximum stresses. Okay. So other examples here at the top left, very similar to what I just showed you, a stepped flat plate in tension. Okay. Here's a round bar in bending. Here is a flat plate in tension with central hole. And then here is a circular bar in torsion with a central hole. Okay. So these create what they call stress concentrations, and we can use this KT factor to figure out a correction for these stresses. Okay, so let's take an example. Let's look at 3.6. Okay, 3.63. Okay, so what we have is a flat plate in tension, and we have 3 holes, and we're going to calculate what the stress is for each hole. Okay, and we're going to use this from appendix that gives you easier numbers to look at. Okay, so if I zoom in here, we have 2 graphs. Curve A is for direct tension on a plate, and curve B is tension load applied through a pin in the hole. We're not doing that right now. Okay, so you see the sketches. All right, we're looking at curve A. But let's go ahead and calculate. How do we do this? Well, first, let's look at, we'll call this hole 1. We'll call this one hole 2, and that one hole 3. So hole 1, we got D is 0.72 inches. We got W is 1.4 inch. Then we got hole 2. D is 0.4 inch. W is 1.4 inch. And then the hole 3, you got D equals 0.5 inch. W is 1.4 inch. Okay. We need to calculate D over W, but we also need to know the thickness, 0.5 inch, and this F is 6,200 pounds. That's going to be the same for each hole. All right, so now let's do this. So D over W equals 0.72 inch over 1.4 inch. You get 0.5. And looking at the chart, we get roughly 2.2. So let's go ahead and look at the chart. So we're at curve A, 0.5. We're right here. And each one of these should be, so 2.2, 2.4, 6, 8, yep, 2.2. Okay? So we just go up from the bottom, and then we go left. 2.2. All right. Again, thickness and F are the same, so let's just calculate D over W. So we get 0.4 over 1.4. We get 0.29. KT is roughly 2.4. And then over here, D over W, 0.5 over 1.4. You get 0.36. And KT is 2.3. All right, now for all of these, in order to find sigma max, you take KT and you multiply it by sigma norm. Sigma max is KT, and the norm is going to be F over W minus D times the thickness. And again, that's based on the shape here and the equation right here for that. If this was curve B, then you'd have to use that equation right there. Okay. And again, different shapes might have different conditions. Different shapes will have different sigma norm. Okay, so let's go ahead and calculate these for each case. So sigma, I'll just call it sigma m. We got 2.2 times 6,200 pounds divided by 1.4 inch minus 0.72 inch times 0.5 inch. Sigma m, you get 40118 psi. All right, I'll do sigma m here, 2.4. I'm going to just skip the units just for time, but I want you to make sure you put yours in. Times 0.5, so sigma m for this case, 2970 psi. And then the last case, sigma m, 2.3 times 6,200 divided by 1.4 minus 0.5 times 0.5, and you get 31689 psi. Okay. So that's how you just got to use the chart. All right, let's look at this one, just a slightly different example. Okay. Here we have axial tensile force. Okay. Again, this is from the appendix. We have these equations over here. So we have given D is 42 millimeters. We have little d is 30 millimeters. We have R is 1.5 millimeters. And F is 30.3 kilonewtons. We're going to look for sigma m. Here's our sketch. And then solution. We got to look for D over big D over little d, 42 millimeters over 30 millimeters. We get 1.4. R over D, we get 1.5 millimeters over 30 millimeters. We probably should put a heading. Let's just put find graph values, maybe. And this is 0.05 millimeters. Now let's use the chart. So the bottom x is 0.05. Let's see, so 5, 6, 7. So it's going to start down there, and then 1.4. Okay, so let's make a line right there, and let's do red. So this is 1.2 and 2. So we're probably closer. We're kind of like somewhere like that, okay? 2.2, that's fine. So KT, 2.2. So now we can find sigma n. Sigma m equals KT times sigma n, the norm. So KT times F over A, those are the equations at the start. KT times F, and the area is pi d squared over 4. Let's go ahead and plug our numbers. So 2.2 times 30.3 kilonewtons times 1 newton. There's 1,000 kilonewtons. Okay. Oh, no, I've messed that up. 1,000 newtons in 1 kilonewton divided by pi 30 millimeters. There is 1 meter. There's 1,000 millimeters. That's squared divided by 4. And sigma m, you get about 97 megapascals. Okay, again, we identified the situation. So we have axial tensile force. All right, this is stepped around bar and tension. We have our KT. We just got to find these parameters here. And then they give you these sets of equations on the graph as well. So these are a couple examples of stress concentrations. Now let's take a look at area shape factors. Okay. So depending on a shape, let me go to the graph here, okay? You may have to, you want to design so it's not going to fail, okay? Different shapes, you will have certain equations that you need to use, which is called an area shape factor. Those are used to help you identify how you would find your design criteria, okay? So if I go back to this example here, we're going to do this saw, and we're going to look pretty much at this point right here. And I'm going to show you the steps on how you design to find a design factor for that particular section so it doesn't fail. Okay? So it's a curved feature, curved structure, and I'm going to show you the steps on how to find your design factor. Okay? And it uses that area shape factor. All right, so in a curved part, okay, so here's a curved section of something. We have a moment that goes up. This is in the positive direction. And if you notice, I'll highlight, see this concentration, this sigma? This is your stress concentration or stress distribution in this curved section. Okay? Out here at the end, this is what we call sigma O, and then in the inner part is sigma I. Okay? So you will get this type of stress concentration as these moments are created on this object. And there's going to be a point right here, okay, which is the radius out, where they're pretty much like your central neutral axis. That's where the stress concentrations flip from one direction to the other. Okay? And depending on the moment, the forces that you're acting on, you want to make sure that you design correctly so this thing will not break or shear or break apart. Okay? And again, depends on the shape, which is that graph I showed you before, and depending on the radiuses, you need to know that. Okay? So you're going to need to know Ri, which is the inner radius, the centroid radius, and the outside radius. Okay? And then you got to calculate your moment. And again, I'm going to show you the steps here with a particular problem and how you do this for a design factor. Okay? So, let's go ahead and do a problem. So here's a saw. All right? It's basically saying that there is 480 newtons being applied to this to tighten this, and it's 80 meters away from this curvature, and this outside radius is 25 millimeters, but this is a hollow tube with the outside is 10 millimeters, the inside is 6 millimeters. Okay, so you're going to notice that we need to do an area shape factor for a circle, and this is the equation that we're going to use, and this is your area. Okay. However, sorry, we have two circles, so you're going to notice that I'm going to subtract the area and I'm going to subtract the area shape factor equations. Okay. So we want to know is 400, oh, I don't know why that wrote that, 480 newtons too much when we tighten that nut down? Is it going to break right there? If it is, then I'll show you what force can we use and how we do that. And I'm going to do that in Excel. I'll show you. All right, let's get started here. So first, I'm just going to erase this just so we can have it. Let's keep it right there. Given. We have F, 480 newtons. We have D, distance, is 80 millimeters. We have RO, which is 25 millimeters. Okay. RI is 15 millimeters. I'm going to show you this here in a second. RC is 20 millimeters. We have D1 is 10 millimeters, and D2 is 6 millimeters. Properties. We're using SAE 1020 cold drawn steel. And we look in Appendix 3, the yield strength, SY, is 352 megapascals. So we're pretty much, we're going to calculate these sigmas and the outside and the inside, okay, because they're at different radiuses, and they will, if you notice, if you look at this shear, they calculate a different stress. And we're going to see, okay, we're going to compare the sigma, the inside and outside, to this and see what the design factor is. All right, we want a design factor greater than 2 typically. So this is cold drawn steel. The yield strength is 352, and I found that in Appendix 3. Okay, now here's our sketch. Here's the 6, here's the 10. And then if I draw this, to give you an idea, going all the way out, that is RO. Here is RI, purple. Out to here is RC. And the way I calculated RI was R naught minus 10 millimeters. Okay, and R naught was 25 millimeters minus 10 millimeters, and that gives us our 15 millimeters. Okay, because it's 10 millimeters thick. Then RC would be 25 millimeters minus 5 millimeters. Okay, it's a centroid of that, so 20 millimeters. Okay, so I just basically took half a 10, and we got that. All right, cool. The last thing I'm going to do is just maybe do a sketch right here. Here is the arc, right? And what's going to happen is we're going to have moments this way, and it's going to be a negative moment, okay? Because it tends to decrease the curvature radius. All right. And this force is being applied, like if I draw out the whole shape, right? There's a curve here, and then here is the nut, right? And then we're tightening it. This is that force, F. As we tighten it, it pushes in that way, okay? So that's the moments that's generated. It is actually opposite of what we have up here. Okay, these are positive moments. They actually straighten out the curve. So you want to make sure your directions are correct. Okay, we set up all this. Actually, the last thing we need to do is say find. And this is N, which is our design factor. Okay? All right. Let's get to the solution, show you how to do this. So we're going to find Ni and No. Ni is Sy over sigma I, and No is sigma Y over sigma O. Well, we need to find sigma I and sigma O. Okay, sigma I is equal to M R minus Ri. Oops, let me do this again. Big R minus Ri divided by A times R of I times RC minus R. And then sigma O is M times big R minus R naught divided by A times R naught times RC minus big R. Okay? So in these equations, we need to find R, A, and the area shape factor, and the moment. Okay, but let's find R first. R is equal to the area divided by ASF. Okay. Again, this is an equation that you will see in the book as you read. And this is that R is that radius right here that is located right at this neutral axis. Okay? All right. So let's go ahead and find A. So A is going to be A1 minus A2 because it's a hollow pipe. Pi D1 squared over 4 minus pi D squared over 4. And we get pi over 4, 10 millimeters squared minus 6 millimeters squared. And the area becomes 50.3 millimeters squared, or 5.03 e to the minus 5 meters squared. Okay, next on the list, find area shape factor. ASF equals ASF of 1 minus ASF of 2. Again, it's hollow tube. Using that equation I showed you earlier, it's 2 pi bracket RC minus square root of RC minus D1 squared over 4 minus 2 pi RC minus square root of RC squared minus D squared 2 over 4. So we're going to plug numbers. Let me do it in orange here. ASF equals 2 pi times 20 millimeters minus square root of 20 millimeters squared minus 10 millimeters squared over 4 minus 2 pi times 20 millimeters minus square root 20 millimeters squared minus 6 millimeters squared over 4. And the area shape factor is going to be 2.59 millimeters roughly. Now we can find R, which is 50.3 millimeters squared over 2.59 millimeters. You get 19.5 millimeters. Okay, next is the moment. So find M. So M equals the force times distance. And this is going to be a negative moment like I talked about before. And I'm going to times it by 80 because that's the distance away. And I'm just going to convert it to Newton meter. 38.4 Newton meter. Okay. Now we can find sigma O. So negative 38.4 Newton meter times 19.5 millimeters minus 25 millimeters. I'm going to divide these both by 1,000 to get it into meters. Divided by 5.03 e to the minus 5 meters squared times 0.025 meters. I converted that to meters from millimeters. Times 20 minus 20 millimeters minus 19.5 millimeters. Divide that by 1,000 to get it into meters. Sigma O, you get 336 megapascals. And you're going to notice, I'm going to show you Excel, that I rounded and the numbers are definitely different. Okay, so the rounding will make... Okay, so let's find sigma I. Sigma I equals negative 38.4 Newton meter times 19.5 millimeters minus 15 millimeters. Divide that by 1,000 to get it into meters. Divided by 5.03 e to the minus 5 meters squared times 0.015 meter. I converted that to meters. 20 millimeters minus 19.5 millimeters. Divide by 1,000 to convert it to meters. And sigma I becomes negative 459 megapascals. And again, my Excel will be slightly different because I'm rounding. So now once we have those, we can find Ni, which is negative 352 megapascals divided by negative 459 megapascals. I put the negative up there because this we want to be positive, okay, 0.77. And then NO, 352 megapascals divided by 336 megapascals, and you get this to be 1.05. So, in summary, if we go to the top, what you need to do is, we're finding this design factor, is you take your yield strength and you divide it by the stress in the inner and the outer to find a design factor. This design factor you want over 2, okay? If you notice here, we didn't. So I'll show you my Excel where you can plug in all the numbers and you just keep changing F until you get the right answers, okay? What you need to do is you need to find sigma I and sigma O. Here's the equations. In those equations, you need to find the R, which is that radius out to that neutral axis where the stresses flip. You got to find the area, the area shape factor. The area shape factor equation, again, depends on the shape. So a square, triangle, circle, ellipse, trapezoid, and there's more. Those are the area shape factors that you have. Okay. Once you find your area shape factor, then you can find that R. You got to find the moment. Make sure you have the right direction. Then you can find sigma O, sigma I, and then finally your design factor and check if it's greater than 2. Both of these, it's not going to work. This is too much force. So the way to do this, to make your life easier, is to make an Excel sheet. Okay, so let me zoom right in here. So this is how I want you to do Excel for me. Header with your name, the homework number, put a description on here, the date. Nomenclature, okay? I'm fine if you just use the basic variables you're using, okay? Force, distance, radius, area shape factor, area, sigma, design factor, okay? Now don't look on these columns, just wait, I'll show you. So here I put my givens, so F, D, RO, RI, RC, D1, and D2, and I converted them to meters over here, okay? Here's my sigma, my SY, my yield strength. Okay, then here I get into the solution. So I calculate my area for D1, I calculate my area for D2. Here is where I subtract the areas, okay? Next, area shape factor equation for 1, area shape factor for D2. Then I subtract them. I find my R. I use my force and my distance to find the moment. So if I click on this, again, I'm using numbers in my givens. So do not hardwire numbers. Like, make your givens and then put the cells in there. And then for sigma O and sigma I, for my life, to make my life easier, I put numerator, denominator, those equations, and then found sigma O, numerator, denominator, found sigma I, and then I went down here and found Ni and No. Now, if you notice, the numbers are different because this is not really rounding. I rounded, so my numbers are going to be slightly different, but they're pretty close. Okay. As you clearly can see, these are not above 2. So how would you do this? Well, I copied and pasted over to these columns. And the cool thing is, all you have to do is keep changing this F until these become greater than 2. Both of them, okay? You want both to be Because if 1 isn't, then what's going to happen is if the inner is not greater than 2, then you're going to have a failure. You might have a failure in the inside of that curvature. Okay. So again, I just copied and paste. I kept changing these numbers here, actually this one here, until I got both of these to be above 2. Now, how did I make it green? Well, if I go up here and I select this cell and I go to conditional formatting, I click it, I go to highlight cells, you can do greater than or less than, and you can pick a color. So if I do greater than, I type in 2, and then this I want to be green, and I click OK, and then it will do that. Then you can go ahead and click conditional formatting, do less than, you can say less than 2, and it'll be red. Click OK, and then watch. When I change this to, say, 500, boom, they both are red. If I change it to 400, then we get still. Okay, let's try 300. Still. Okay, 200. There we go. 200, you get NO is okay, but NI, it's not designed right. So here, this is an example of stress concentrations and design factors for you to help for homework 2. Best of luck, and if you have questions, let me know.